It works.
Hello. Hello. Yeah, I shouldn't have the puffing issue. I you didn't hear nothing. Hello. 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 Yeah, I shouldn't have the puffing issue. You didn't hear nothing. Hello. 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 Yeah, I shouldn't have the puffing issue. You didn't hear nothing. Hello. 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 Yeah, I shouldn't have the puffing issue. Have the puffing. Hello.
Test,
Green is mute, blue is on.
test.
It can't be too far away. It can be a little bit far away, but it can't be too far away.
But also can't be too close.
If it's too close, then there. Test. Can you hear me on the speaker? My voice is acting. Good. Good. Can you hear it on the speaker? Yeah. Is it picking it up? Hello.
Hello. Hello.
Okay. How's it too far? Do you want me to attach it to my neck? I'll do a turtleneck. Note to self, always wears turtlenecks.
But when you bring it up close, it starts popping.
So you can't have it too close.
More pronounced on the speaker. The speaker is not working nicely. So what's your suggestion? Just hold it here or hold it down here? Hold it here. Yeah. Test.
Sorry. Whom?
No, not this one. No, not this one.
Never had it.
Hello. Yeah. Whenever. Well, I'm hoping so, but yeah. Us. Yeah. Yeah. I guess like okay, so for, like, we'll see how it goes. Yeah. All right, so I think we'll get started. Um, People might join like here and there, but that's fine. So yeah, anybody who just showed up, feel free to scan the QR code and enter into the Google form so that you can win either one of these really nice engineering plaques, or you might be able to win a gift card. Yeah, without further ado, I'll just get started. So this is this is our plan for the event today. We're going to be starting off with professor presentations. Cora and Rama in the back. And throughout these presentations, you're going to be able to learn a lot more about the different civil engineering subdisciplines. We're specifically touching on geological engineering, water resource engineering, and environmental. Following this, at around 3:05 to 3:55, we'll break off into our parallel sessions. Here, you can choose to pretty much attend any of the presentations you want. You can switch between the two. We have the opportunity to meet James Byrne back over there. He's an engineer in the industry. And so he'll be in this room speaking about his experience in the engineering field. You'll also have the opportunity to meet two co-op students, myself and Yusra Sani, she's outside. But you'll have the opportunity to meet us, ask us some questions about the co-op program and our experience in the Lassonde Engineering Co-op program and the whole process of going through that. And then at around 3:55, we'll have our parallel lab demonstrations in version 115, where we'll have two lab demos, one pertaining to lights used for water disinfection, and then another one pertaining to geological process. All right, so just before we get started, I wanted to get everybody's like minds thinking about civil engineering. So can anybody tell me what civil engineering is? Not a professor or industry professional, preferably, but anybody want to tell me what they think civil engineering is? Go ahead. Designing and building stuff. Okay, pretty valid. Anybody else have any ideas they want to share? Okay, you're pretty much like on the ball. Civil engineering is the design, construction, and maintenance of structures and infrastructure in both the physical and natural environment. So essentially, civil engineering pretty much encompasses all of the structures and infrastructure all around us. That can be anything from the earth itself, the layers in the earth, all the way to man-made buildings and bridges. So it's a very broad field, which is why civil engineering is often divided into many little subdisciplines. Some of the subdisciplines that you'll usually hear about include geological engineering, environmental engineering, water resource engineering, transportation engineering, and structural engineering. So these 5 main subdisciplines are the subdisciplines you'll usually learn about in your upper year courses. If any of you in this room decide to pursue civil engineering as a major, you'll have the opportunity to take courses strictly pertaining to these fields of study so that you're actually able to really explore them to their fullest potential. All right, so now that everybody has a little bit of an understanding of civil engineering, I will turn it over to the professors. Dr. Matthew Ferris, would you like to go first?
All right, so get mic'd up. Hopefully you can hear me okay. Whoops. All right. So I'm Matthew Para. I'm a geological geotechnical engineer by training, and I'm also the undergraduate program director of civil engineering. So if you have any questions at all, do reach out and send me an email. My email address is at the end of the presentation, so you can take it down, or you can come by the 3rd floor of the Bergeron, and the lovely ladies at the entrance there will direct you to my office, which is just down the hall from the main entrance of the civil area. All right, so welcome to Declaration Day and welcome to civil engineering. We've already had a nice introduction to civil engineering. Whoops, that got shifted a little bit. That's okay. So I'm going to talk a little bit about myself and then the department and the program in a little more detail, a little bit about my research, and then some time for questions at the end. So I started off studying geological engineering at Queen's University. Don't hate me for that. And actually, I went into general first year, much like yourselves. And I got a job after first year at a quarry in my hometown. My best friend, his older brother worked there, and he just kind of got me a job, and it was the best paying job in the neighborhood. And that's really the only reason I took on the job. But actually, it transformed my life, actually, and got me onto the area of geological engineering, which is very closely related to civil engineering. And I went on to switch my major. I was going into aerospace engineering, switched into geological engineering. And after that, I graduated and I started working on the Niagara Tunnel project. Has anyone heard of the Niagara Tunnel project? Yeah? Great. So this is a major project down in Niagara Falls, Canada, to divert some of the water from above the falls and use it to generate more hydroelectric power. Actually, hydroelectric power really has its birthplace in Niagara Falls, and some of the earliest hydropower stations were constructed there, and there was an expansion, and that really was my inspiration to go on and do more research. And so I went on to do research, because the tunnel, this is the rock above where the tunnel should be. The tunnel should be about here. And we had, in this picture, it's almost 4 meters of overbreak, rock falling down that wasn't designed to, we didn't want that to happen. And it got up to 6, maybe even 8 meters at times. And I really wanted to know why that was happening. So I turned that into a master's thesis. And that led me into doing some research in my PhD for deep geological repositories, which utilize the rock as a barrier. And this is an example of a layout underground where we can put waste and seal it into the rock. But if your rock's doing this, it's not a good place to seal it up, right? Because all the fractures and broken rock is obviously not good. And so I tried to use the knowledge I gained from my master's in my PhD. And I've gone on from there to do research here at York University. Underground, I'm looking at a lot of instrumentation data. So this is a collapse above my head that happened. Actually, this is a tomb in Egypt in the Kings Valley area. And we're measuring the deformation of this area that's collapsed and seeing if there's actually any changes currently happening, because the archaeologists, they want to open up this tomb for tourism. And obviously you don't want tourists to come in there and have problems with rocks falling on their head. I also look at cliffs, and this is also the Kings Valley in Egypt. And I'm looking at environmental influences that can lead to crack growth in rock. So that's some of the research I do. And I actually partner with many people in the department, such as Liam Butler, here is professor in structural engineering. We have just developed an outdoor testing facility where we can test samples. Like here, this is actually a 3D printed sample trying to replicate sand or just a fancy geoid and other samples that I like to bring to class to show off stuff that's from the real world. So we could test some of these things outside, look at how does the daily heat fluctuation or rain or wind impact the behavior of these samples. So that's some of the research I do. And so the Department of Civil Engineering, it was established in 2013. We got going with our first undergraduate students in 2014. Currently, we have 19 faculty members, 6 female and 13 male. And we have a lot of state-of-the-art physical and computational labs, and that outdoor lab testing facility is one of a kind in Canada so far that we're aware of. And hopefully we'll be able to get that up and running soon so we can use it for teaching and research. But here also, the pictures on the lower left, that's the high bay structural lab. We can test, full-size wall segments in that lab. We can compress them. We can do earthquake loading simulations of various things. And then this is an example of taking climatic influences such as rainfall and seeing how that impacts the infiltration into various substrates, such as this earth embankment illustrated here for the rail line. And then the moisture that actually enters the soil changes the properties, and you can have shrinking or swelling of the rock and soil depending on material. So we can model these things and this kind of behavior. You can also model the structural wall behavior as well. And these are things that you'll actually touch on in our undergraduate program, both physical testing and numerical modeling. So our department has 3 main pillars that influence both our teaching and our research. And that's designing for climate change, infrastructure and resilience, and sustainable development. And those pillars rest upon a foundation of those 5 subdisciplines of civil engineering that make a strong foundation, and pun was intended there, for our program, our undergraduate program. And so these areas are structural engineering, geotechnical or geological engineering, hydrotechnical engineering, and transportation engineering, as well as environmental engineering. And in no particular order, you've probably heard of structural engineering. You've probably, half of the room or more is probably here because they want to design bridges and buildings. You want to raise your hand if you're interested in designing bridges and buildings? All right, sort of, maybe, hard to say. All right, but a lot of the things that we also teach you go much beyond just, bridges and buildings, right? In environmental engineering, we are looking at getting clean water, okay? We're gonna need to clean up municipal wastewater, but there's also a lot of other aspects of environmental engineering that you'll hear about in a few minutes on the next 2 talks. Geotechnical or geological engineering, that's dealing with, natural materials, earth, soil, and rock, right? And building on them or in them or with them, right? And structural engineering, often we want to design these beautiful structures, these interesting structures, but there's a lot more that goes into structural engineering. We have to, study the materials that are being used, right? And we have to to touch on sustainability, we need to study and research new materials, emerging materials to meet the demands of society and industry to build such advanced structures. And in hydrotechnical engineering or also water resource engineering, there are many aspects. This is dealing with the flow of water, structures that interact with the flowing water, but also researchers in our department are looking at the flow of microplastics in our water. So they're going and doing multidisciplinary research. And finally, transportation engineering. This is more than just building roads or bridges, okay? We have some experts in our department. They study the flow of traffic, okay? They study the flow of transportation and goods. And they actually have quite advanced software to look at that flow of people, of products. And even during the pandemic, they actually wrote a nice little paper about social distancing. They were able to actually simulate social distancing in their software and look at different methods to encourage the population to social distance, and they could actually simulate that. So there's a lot of physical lab testing that goes on in all of these areas, as well as numerical modeling. Wrap it up. Okay. So civil engineering program at a glance, we touch on those 5 subdisciplines, as well as a lot of design, math, chemistry, physics. And you can see by the colors that in later years, we get into more focus on those 5 subdisciplines. And we also have a lot of choice for you in your final year. So we give a good foundation in all those 5 subdisciplines, and then in your final year, you get to choose which area you would like to focus on. And we have a range of technical electives to choose from. We're short on time, so I won't do too much on terms of the specific courses, but in second year and third year, you get a lot of hands-on experience. If you want to go to the YouTube channel Geomechanics, you will see me giving you welcome to the classroom lectures. I developed these during the pandemic, and I'm outside in the field. I'm at a riverside. I'm at a mine or a quarry, and I'm showing the class. I can't bring you there, but I went there to bring you that experience, okay? And that's just some of the hands-on experiential education we try to give you. And in 4th year, again, you have a lot of choice, these technical electives to choose from, complementary electives, building up to your capstone design project, which is the 2-term project. And this is one example of a multidisciplinary project. This is the Portlands area, downtown Toronto. And there's so much civil engineering. They're revitalizing this area, changing the flow of the water course, try to renaturalize it to make it more natural. Because this used to be a big industrial area, which means there's a lot of soil contamination that needs to be dealt with. They want to build up this parkland, so we need to get public transit there. We need to do the bridges and so on. All right, so in terms of my research, I think I already addressed some of that. There's some cool stuff we can talk about later, but I do a lot of machine learning because we collect a lot of data. We have an expert in the department who does machine learning. And in terms of my research in Egypt, we're trying to go back as far as we can, even into the ancient records. And in order to do this, machine learning is quite an advantageous tool to compare information from present, where we're collecting an enormous amount of data, every 10 or 15 minutes, to ancient records where we may only have one recording, in some ancient literature every 100 years, okay? So it's very multidisciplinary, interdisciplinary research that we do in the department. I think my work speaks to reflects many other researchers in the department working together, many disciplines coming together. All right, so don't forget to look at the civil engineering website to address some of your questions. Subscribe to the YouTube channel if you want, not pushing that too hard. And email me if you have questions about civil engineering. I would love to get in touch with you. Come by my office and we can chat. Thank you.
I'll do my best. Okay. Like nothing's ever designed for my kind of clothing.
pharmaceutical like anti-inflammatory drugs, anti-epileptics like carbamazepine and diclofenac. So we're trying to measure all these different diverse chemicals in water sources. What are the levels? And also we are using this mm, underground water to test the petrochemicals, like gas stations release a lot of chemicals that enters into the water, groundwater. So we're trying to measure these as well in these water sources. And the cool part that we are currently working with microplastics, we are trying to develop the efficient methods to measure these microplastics in water sources. And these are the successful projects. We developed some treatment technologies so far. We are trying to develop membrane systems. Membrane systems are usually remove absorption process to remove these chemicals, but we are trying to impregnate these membrane systems with biochar and enzymes so that we can absorb at the same time, we degrade these contaminants at the same time. So there are like two nanosystems and microsystems using biochar that developed at lab scale column levels to focus only on emerging contaminants like pharmaceuticals. So we are trying to explore these other chemicals as well. So this is another bioremediation. We are trying to use enzymes instead of like chemicals. We're trying to use enzymes to degrade this contaminants, the harmful chemicals in different sources. Like we try to produce the enzymes, we use the crude enzymes so that it makes less cost, and use this crude enzymes to degrade this unconventional oils or petrochemicals in water sources or soil as well. So far we are working on different sources like wastewater, surface water, as well as petrochemicals in ocean as well, and landfill leachates. This is the journey we start. Our group started working on this contaminants since 2010, and we are focused mostly on pharmaceuticals. And right now we are a little bit diverse to get in touch with other chemicals like perfluorocompounds and petrochemicals. And right now we are working on microplastics as well. So here's one more my colleague who's postdoc, who's leading the biotechnology side. Unfortunately, he's not here to present this, but I'll go through on this. Can we skip this maybe?
It's just for the time.
Oh, okay.
Yeah.
So this is like we use feedstock to the user source for developing some enzymes to make it like a value-added products where we have application in the real time, like plants, biohydrogen, or maybe lipids to come into circular economy. That's it. If you have any question, please email to this email. Glad to answer that. Thank you.
Thank you so much. So just before we get into our meet and engineer presentation and our co-op panel, I was just going to do a quick raffle for one of the plaques. So I'll just do it like this because I don't want to have to use the other computer to do it. Ethan, you'll be my witness. Okay, there we go. Claudio? Claudio? Anybody? Here we go. Okay. All right, so you can win the rest of the plaques throughout the rest of the presentations today. I think we'll be giving the rest of them out throughout, like if you participate during our co-op Q&A or during our meet and engineer presentation. And then with the gift cards, we'll be doing the raffle at the end of our presentation, and we'll be contacting you after the event is over. So without further ado, James, feel free to start your meet and engineer presentation. And here we are. And anybody who would like to join the co-op Q&A, you can follow me and Yusra. We'll be heading up to the sandbox. Thank you. Okay. And then I'll come back. I'll come back later. So I will come back. That's
Yeah,
what I can.
Got the mic. Hopefully they hear me. Oh, yell. Yell. Oh, yeah, please. Whatever. So first of all, I'd like to thank you guys for having me here. You know, it's great to come out here. It was great to hear your professors talking. I'm actually going to be talking about some very similar things. So I'm actually going to go off my regular script a little bit. So we'll talk a little bit more about some of the stuff that I've done and the stuff I'm doing currently. So first, my name is James Byrne. So I'm the GIS lead, and I'm also a partner at GM Blue Plant Engineering. So I do have 24 years of experience. So I've been in the field for a while. I have worked both in public and private. So I've actually worked for the city of Niagara Falls, worked for the region of Niagara, I've worked for the city. As well as on the private side where I worked for other consulting engineering. And basically I've essentially been a client as well as a consultant. I've also done field work. So I've done plenty of work in the field. Lots of people used to say like, oh, it's great. You get to work outside all day, you know, it must be wonderful and stuff. And yeah, but also on days like today where, you know, it's kind of freezing sun, I still have to work outside. So it's like, oh, okay, there's a bit of a trade-off here. But no, so I've done a lot of field work. I've also done a lot of work back in the office, you know, on the analytical side. That's generally speaking what I do now most of the time. So I send other people out in the field. I do make it a point to stay up to date on a lot of GIS. We'll be talking about GIS and data management, stuff like that today. And all the technology trends. And we'll be talking about this in context of what your professors are talking about as well. So it was very interesting to hear them chatting because just to go a little bit into my background, I did actually start in geotechnical engineering. I used to do boreholes and soil samples. One of the largest projects I worked on was actually how many people are familiar with Hamilton? Show of hands, few people. The Link 403 interchange. So I was one of the leads on that when they were actually doing that. So I actually pulled out a lot of core samples, core samplings. I've done a lot of environmental work as well. So if you have questions about how some of the environmental stuff works, I can certainly help that. But no, so information management, you know, best practices, trends, technology trends, that kind of thing. Evolving data collection methodologies. So there's lots of different ways to collect data. Data is becoming king these days of everything. So we will talk about that in a little bit. Various applications and languages that I know as well. So, and then also technological integration methods. So a lot of the stuff that you're going to see, and I'm going to be showing you two things. One package is not going to do it. And if you try to do everything just on using one package, you're probably going to run into some problems. Knowing how to make packages talk back and forth with each other is a very good thing. I am very passionate about this. I really enjoy data. I enjoy the problems. I enjoy the challenges that come with it. So has everyone taken like the legislation and ethics yet? Not yet. Okay, you guys haven't taken legislation and ethics yet. You will. So I'm going to make one minor correction. I am not an engineer. I am a licensed engineering technologist. What that means is I have what's known as a limited license with the PEO. So where an engineer should only practice in areas for which they're competent, I may only practice in areas for which I'm competent. So I actually have a set little box of what I'm allowed to do engineering in. And yes, I do have a seal, so I can still stamp stuff as long as I'm practicing within that area of expertise. So I'm also a CET with OSET. I'm also a member with the Institute of Engineering Technology in the UK. And then you can see I've also got some certifications in GIS. So geomatics management, GIS, GIS professional. I do environmental work as well, though, so I do have my environmental professionals certification as well. And I'm also certified with NASCO. So NASCO is specifically detailed with sanitary systems, sanitary sewers, that kind of thing. As was discussed before, there are a lot of opportunities for yourselves and others to volunteer. So I do actually do a lot of volunteer work as well. So I'm actually director at large with East Basin ERISA. Currently secretary treasurer with the Association of Consulting Engineers of Canada. I chair some of the committees for NASCO, and I also chair a committee with the Canadian Institute of Geomatics. And I'm stepping down this year, the Ontario Public Works Showcase, Technology Showcase. So if you do have any questions about this kind of stuff, anything about volunteering, there are tons of opportunities. A lot of these organizations, they're always looking for people to volunteer. It's a great way to get your name out there, a great way to meet people that you'll want to get to know and work with. So a little bit about GM Blue Plan. So this is the company that, like I say, I'm a partner and I work with. So it is all employee owned. We do have 7 offices around Southern Ontario. So this is where most of our work is done in Southern Ontario. We do actually do some work though in the States. We do some work abroad. We also do some work in Halifax, Nova Scotia. We do some work in British Columbia and Alberta. Somehow we skipped over Saskatchewan. We have about 240 staff, give or take. So we're all professionals in one capacity or another. And we offer what's called a full engineering life cycle consultant. So what that means is that everything from conceptual to, I think I want to build a thing. We help people with that. Once they've determined that, yes, this is the thing I'm going to build, we help them with where it's going to be, how it's going to be hooked up, how is it going to be designed, how is it going to be hooked into the existing infrastructure that's in the area, all the way to, okay, now let's actually build it. So we actually work with clients on that. We also work with them in terms of full life cycle accounting. So as I'm sure we're all aware, how many people have a car? Really? Okay, interesting. I thought there'd be more. Honestly, I thought there'd be more. But no, so you buy your car for, I don't know, let's say $20,000. Obviously, that is not the cost of the car over its life cycle. The car costs, $20,000 to buy it. It costs another bunch of money to maintain it. It costs more money for your oil changes, your gas, all that. So we do help clients understand that when they actually have an asset, they get an asset in place, there is a cost associated with maintaining that asset over time. So we do actually have a dedicated team of 12 GIS and data management staff. And we are, of course, backed up by all the industry experts for a lot of the data collection, as well as a lot of the engineering. So one question, we asked a little bit about this, what is civil engineering? So I'm going to go, who can I pick on? Who answered the first question? Cool, we'll pick on you again. In a broader sense, what would you say engineering is? Not bad. What if I went a little bit broader and said that it's to protect the public? Oh, that was good. Should have been private public interest. But to protect the public interest. So there's a lot of things that go on. A lot of it is engineered. And one of the roles of an engineer is to make sure that the public is protected. Another thing, again, this is very broad, problem solving. That is I'm going to say, in my opinion, that is the heart of what engineers do. They problem solve. People come to engineers with a problem. Why did they come to you? Because they feel that you can solve their problem. It's also innovation. So obviously we all figure out how to solve various problems, but being able to innovate and say, you know what, there is a better way. I've done this testing, I've done this research. Why don't we solve this problem in this manner instead? It's better for the environment, it's more economical. So in general, like I say, that's my idea of what engineering is from a very general, very broad. Now, when we look at data engineering, so first of all, there's data and information. We'll talk about, there is a difference between the two of them. We will talk about that. Another part is analytical modeling. So you have your data, you have your information. What are you going to do with it? Well, then you got your analytical modeling. So this is stuff that, again, your professors were talking about, where you're going to take that information, you're going to actually tell the computer to do some stuff with it, because you want to test it out. You want to see, what'll happen if we do this, what if scenarios, things like that. Then, of course, there's application development. So I go through this, I've got information, I've got it modeled a certain way, and now I actually want to apply it. So, okay, how am I going to apply it? How am I going to get that out there and help other people, help other engineers, help the public understand and use this information? So when you bring these two things together, generally speaking, It's all about putting the right information in front of the right people at the right time. That is the overall goal. That's my overarching goal for what I'm trying to do. Whoever that person is, I need to make sure that the information is in a manner that they can understand. I have a friend who's a nurse, for example, and she tells me blood pressure stuff like, oh, it's 80/20. I have no idea what that means. So that is not good information for me to know. I don't know, the person could be dying, they could be healthy. I have no clue. She totally understands what that means. So providing that information to her at the right time can help her understand what's going on with the patient. Any questions about any of this so far? No? So when it comes to data management, I did not come up with this. I just put two things together. I'm sure we've all heard this before, knowledge is power. This is very true. Like if you actually know what's going on with a system, if you have all the information, then you can start manipulating that. You can start understanding how to actually work with that information. So the appropriate management of data leads to information, and that's the difference between data and information. Data is very raw. So there's lots of information that comes in. I used to get information from automatic vehicle locators. So these are the GPSs. So this is like GPS in your phone that people would have in their vehicles. So I used to receive all that data, and it is just data. It says I'm vehicle number 1, 2, 3, and here's my lat long and elevation. Generally speaking, we also had here's my speed. And that would actually ping out every 5 seconds. So every 5 seconds, as you can imagine, when I had a fleet, I was looking after a fleet of 26 vehicles. 26 vehicles every 5 seconds pinging out, that is raw data. That means nothing to anyone. It's not fun, it's not good. When you actually take that data and actually start processing it a little bit, then it becomes information. So when I actually started looking at it and say, you know what, I just want to see certain trucks. I just want to see certain vehicles. And I only want to see it, when they're going over the speed limit, for example. Okay, now we're getting some information. I only want to see when they're over the speed limit and perhaps when they're stopped for more than, I don't know, 10 minutes. We'll see what's going on. So that starts to bring up more information. Then I can start looking, okay, why is this happening? Is there a good reason for it? Yes or no? So when it's given to the right person at the right time, that leads to knowledge. That's when I can actually say, okay, you know what? We're not spreading salt on the roads properly. Not plowing the roads properly. So I can actually figure that type of stuff out. So this in turn leads to decisive and defensible action. So everything has to be somewhere. That's the other little thing. So there's lots of data, lots of information. All GIS does is it brings in that locational component into things as well. So you can basically put that in there just as another piece of information. So a lot of the stuff we do, how did I get here today? Like most people probably called up Google and said, hey, Google, I live here. How do I get there? It figured out what's the best route because it knows all the routes, it knows all the traffic, it's receiving all the data, it's processing it into knowledge. So everything must be somewhere. There's a lot of information that come out with the spatial component. So a few things for consideration though, when you are working with information. Hard drive space has become very cheap, but storage of data should remain independent of the input and output. So obviously, if I store stuff on this computer, that does you no good. So I should make sure that, well, if you need to access it, it's stored somewhere appropriate that you can actually access it as required. Analysis should be prepped and conducted via query sets. So for example, a lot of that information that comes in, I don't go and change that information. That would be a bad thing because now I'm actually manipulating the data as it came in, and I can't go backwards that way. It can also be a bit of a legal thing. Some people can say, well, what did you receive? And if I can't show what I received, then that's a problem. So what I do is I build query sets. I actually just ask the computer, you know what, leave the data as it is. Please run this query or this analysis on. Even if that means duplicating the data, I mean, sometimes that happens as well. Sometimes it's appropriate. Output should remain independent of both of these. So like I say, if I need you to be able to see it, I should make sure that these two things are actually happening somewhere that works out and is independent. Appropriate documentation is a must. Yeah, I'm going to say documentation. Generally speaking, nobody likes doing it. I don't like doing it. My staff don't like doing it. Nobody likes doing it. However, it is very, very important. Generally speaking, we have a particular rule. It's a 5-year rule where pretend someone who was not involved in this project is going to be looking at this stuff 5 years from now. Will they have enough information to figure out what was going on? One of the main reasons why we use that is because usually about 2 or 3 years from the project, I'm looking back at my own work, and it's really helpful for me to be able to understand what it was that I was doing. I've had a couple of funny times where I'm actually looking at something going, hey, I don't know what's going on, but wow, this looks really good. And it's actually done pretty well. And I'm pretty impressed. Hey, I figured everything out. This is awesome. Oh, hey, I'm the guy who actually made it in the first place. So it's like, okay, I need to improve my documentation a little bit better. And like I said, we've already talked about data versus information. So data management toolbox, like I say, some people like to just have one tool. That they feel the need to just do this thing in one tool. They're just going to use CAD. They feel they have to use AutoCAD. That's what they're going to use, or they're just going to use ArcGIS, and that's what they're going to use. I say that that's a bit of an error because number one, one tool is not always the best tool, and as you can see, sometimes it's very much. So it's very good to have a toolbox. It's very good to know that, okay, you know what? Here's a variety of tools I can use. Different things. I can move things back and forth, move things around. Usually that way you can actually find and make sure that you have the best tool for the job that you're trying to do. Often I save a lot of time because, believe it or not, it's actually easier for me to take something out of tool A, bring it over into tool B, do my work and bring it back into tool A than it is to try and actually do everything in tool A. But why stop there? Should always be willing to look at all the tools that are available. If someone comes up and says, hey, I've got this other wonderful widget that might be able to help you, check it out, look at it, see if it works for you. Will it work in your workflow? This happened to me recently. We've been using an application called Survey 123 for the longest time to do field inspections, field reports. Someone came to me and said, you know what, there's this other one, it's a bit of an unknown. It's out of the UK. Said, you know what, we'll give it a shot. We'll try it out. Best thing ever. Workflow, much smoother, works much better. We're totally happy. It's also cheaper, which is also a nice thing. So generally speaking, in a lot of your courses, you're going to learn a lot about, I'm going to call it the mainstream applications. So the AutoCAD, Microsoft Office, Esri, stuff like that. I'm going to talk a little bit about open source. So open source is not really talked about a lot. I do encourage you guys all to try it out, look at it, download it, try it. They usually have a very rapid update cycle. So you can actually get some pretty cool things coming out very quickly. It is considered to be more open for collaboration for the most part. And also integration with other open source projects. So a lot of projects use the same libraries, which means that if you have tool A in open source, you can usually talk to tool B in open source. So there's obviously more options and more variety when you're doing this. And you can also get more tailored solutions that actually work much more towards what you're trying to do. There's a small list there of ones that, like I say, that I use a lot. So one of the ones we're going to be talking about primarily is going to be Vue.js. So a little bit about that. I'm not going to go over the whole history, but basically, it does actually have some dedicated support. They did do a major recode when they got to version 2. One of the main things I'm going to point out is that it is free. So free meaning you can download it and use it for whatever you want. I can use it for commercial stuff. You guys can use it for educational stuff, research stuff. Totally free. The last time I checked, it had over 1,200 plugins that were available and counting. It has over 1,000 modules actually installed in it. So there's lots of stuff that you can do with it. Installation, a couple of nice things. One of the nice things is that it'll actually work on pretty much everything. So it even works on Android. There's a 32 and a 64-bit version. One of the things that I really like is that previous releases are available. And this also means that they can live side by side. So I'm sure we've all had this happen to us before where you install some software, you're using it, they update it, something you're doing is now broken. The nice thing is you can actually upgrade and keep a separate copy running side by side. So which is really nice. So this is generally speaking what it looks like. So I was able to actually find a little song center. So turning data into information. So the next little bit is just going to be a bunch of case studies. So this is where we've actually used this to actually start building things. So obviously one of the main things you can do with the GIS is you can make maps, so which is cool. One project we did for Ottawa, though, we actually looked at all of their facilities. These are all the city-owned facilities, city-run facilities, what they do. And we looked at a bunch of information about basically how was it doing it, what would happen, what would the risk be if you were to remove that facility. So, and we looked at things like, for example, I used to actually live down here. So if you actually we have an arena down there. If you take that arena out of service, that means that someone has to drive from there all the way into the city to actually go skating, do hockey, whatever. So that's a problem. Obviously, if you take an arena out of service in here, not as big a problem. So we basically went through and started indexing, you know, what's the risk, what's the benefit or detriment to the public with all these facilities and their uses. This is for the city of Brantford. So we actually did a linear assessment. So what this does is basically, we did two things. We looked at all of their main linear infrastructure sets. So road, water, sewer, sand, and storm. We actually graded them all. So how good is it? What's the risk to this piece of infrastructure? And risk is defined basically, what's the chances of something going bad on it, and how bad will that be? So those are essentially what the risk model is. And you can see here, we actually plotted it out. So anything that's getting up into that range, that means that the chances of something going wrong is high, and the effect on people if it goes wrong is also high. Down here, that's completely the opposite. Chance of something going wrong, very minimal. Even if it does, no one will notice. So generally speaking, you want more things to be in this area if possible. We did a little bit of 3D modeling for it as well, a little bit of coding. The other thing that we did though is we actually took this and we took the information, broke it into corridors. So we actually said, okay, it's nice to know how each individual piece of infrastructure is working, but how are they doing all together? So basically, I'm sure we've seen this before where brand new road, someone goes and rips it up because, oh, the sewer's having a problem. So by this, we're actually trying to work out, you know what? You're planning on replacing the road. Why don't you do the sewer at the same time? And basically working on it all together. One of the other things that we do as well when I work with our water modelers is permeability studies. So this is an area where basically we wanted to find out how much area percentage wise per parcel, per land parcel is permeable versus not. So you can't see it too well, but this is a color aerial image. So you can see the green areas. So generally speaking, things that are green, ground is probably permeable, water will seep into the ground. Areas such as this, parking lots, the water's not going to seep into the ground, it's going to find us hopefully a storm sewer somewhere. But basically wanted to find out what the percentage is. So in doing this, we actually did a bit of analysis. So what this is the infrared band. So looking at the aerial imagery, the infrared band actually works out, the whiter it is, the more generally speaking alive the item is. So you can see now where buildings are coming in darker. And when you actually push that to extreme a little bit, so you do a little bit of massaging with the information. So if I had different information or better information, I could actually work out clay versus soils versus that, anything else. For this one, I just went with true and false. So basically, if it's green ground, then it became white. If it's not permeable, it became black. So that's a raster image. So like I say, that's from an aerial image. So then we told the computer to basically, because I wasn't going to do this, we told the computer to actually digitize it all. So it actually turns it all into vectors. So these are now actual polygons. You can see here, you can't read really well, but there's what's called digital number with that. So it's either a 1 or a 0, it's either permeable or not. And then there's the area of that. This is something I can use now to actually go and slice and dice it based on whatever I'm looking for per parcel. So I can now say in this parcel, this much of it is permeable, this much is not. And you can see how it actually gets pretty accurate because you can see how basically I do have front yards. I've got sidewalks going through as well. Another one that we did that was more of an environmental one was a tree canopy study. So for tree canopies, it was very interesting because we have a lot of information about the ash beetle, stuff like that. So they were also trying to improve their overall coverage. So we started looking at what was there. What you're looking at here, so this is the town of Pelham. This is sort of the major intersection, so to speak. The reddish areas you're seeing, so this is what's called an NDVI, so it's normalized differential vegetation index. That's a fancy way of saying that basically things that are living, things that are green, they come up with more of a red. Things that aren't come up with more of a blue. But so we took that. Now, problem is that doesn't really help me a lot with what the overall area is, because there's a lot of other things, because like say, this picks up everything that's green. They just wanted trees. So areas like that, where's another one? Ones like that, those are actually grassland. So unfortunately to the computer, grass looks a lot like a tree. So we got more information. So using LiDAR. So LiDAR is light distance and ranging. That's basically shooting a laser and actually trying to get a 3D profile of things. This is what's known as a digital train model. So this, you can see here, this is basically a 3D model. In the software, I can actually manipulate it and look at it, rotate it and everything. But you can see now I've got very much, here's the trees versus my flatlands. Now, talk with the client, we all agreed that we're talking trees of significance. So basically trees that are more than 2 meters tall. So this is the digital surface. So this is without anything on it. When you put them together, what I have left are trees. Everything else has now been basically zeroed out. One of the issues I did come across, which I thought was interesting, I was trying to figure out what the problem was, are these lines that you see that are kind of going across. Any idea what they might be? Yeah, I honestly, at first I thought, is it an anomaly? Sometimes satellites pick up funny things. I don't know. And then it occurred to me, oh, right, hydro lines. So we were able, since hydro lines, those are a known thing, we were able to get those out. And then I was able to, you can also see in here as well that I do still have, obviously, buildings are taller than 2 meters. You can see I do still have building tops. So I was able to isolate those and actually say, okay, so here are now all of the trees. And then I was able to bring that in with the, can't see too much on here, but with the actual building, building outlines and building footprints. So using this, we were actually able to calculate, here is the actual tree canopy area, in meters squared. So this they can now use when they're applying for grants and everything else. One thing that does still come up every now and then, my boss is really fond of offering this service up, is map books. So I do still have some clients that say, you know what, we're sending staff out in the field. And I say, cool, that's awesome. I can tell them to bring a tablet. I can make a really cool little map for them to use and they can pull up the data and stuff. And then they say, no, they're going out in the field with a clipboard. Oh, okay, fine. So I have to make a map book. And one of the things that they asked was they said, we need a map book made. So, go from page to page. Okay, yeah, I can do that. Then these are actually drainage areas. Then they came back and said, well, we need the map book actually to be one drainage area per page. And that was a little interesting because, well, the drainage areas, they're obviously not the same size, and how am I going to set this up? But with a little bit of coding and stuff, so we had a little bit of coding, we're actually able to make it so that, and if you watch the map carefully, so if you watch like the scale bar, for example, they do change for each different map. So now we were actually able to create and prepare a map book that staff could use out in the field, and it is actually individual per drainage area. The thing I really liked about it was the fact that it was like, oh my God, this is great. It must have taken you so long to do. Yes, it did. It took me forever to do. No, it took, actually, once I got it figured out, it probably took about half an hour. Field data collection. So like I say, these are some of the new things that are coming up. So this is an application that we use. It's called Mergent Maps. So again, it is an open source application. You can use it for free. We have a commercial license for it. So we actually do pay some money for it. What you're seeing right now, this is actually what it looks like on the phone. So we actually have staff that are out there using their phone. When they tap on something, they get a nice little form. The form is something I actually made on the desktop. So everything's in sync. And so everything works out on the desktop the same way. So you can see the map on the desktop looks the same as the map that's on the phone. This means that the workflow is much simpler. When they're actually entering the information, we have lots of stuff set up for drop downs and calculations and stuff to make it easier. So less typing is always better. Although we have found that the voice to text actually works pretty well. But then they can also take pictures as well. So they can take lots of pictures, as many pictures as they want, and they all show up on the project the way they're supposed to. Project and program management. So this is something else that came up with one of our clients. Those are all manholes. And this is where we initially made a map book. So here's the grid for the map book. And that's what the map book pages look like. And we put a little bit of code in there. And I know it's difficult to read, but we basically set up rules so that if we have some of the rules, if the depth is less than 7 meters and it's not a specific type of manhole, it gets flagged a certain way if it's other things. So this allowed us to actually do our reporting very easily, because then I can say, for example, 737 of the first one, there's 1060 of the second one. So this makes actually managing a project and program very, very simple and very easy once you get the logic worked out. So we actually spent probably about 2 or 3 days to get the logic worked out, but this saved us probably about 5 hours every time we had to make a report. Reports are 2 weekly, so this saved a lot of time. Profile mapping is something else that comes up a lot. So these are potential routes for a sewer. And it was decided that this one was the one that was of interest. So we actually had elevation information. And using that, we were able to make a digital elevation model. And using that, we were able to make a profile. So here's the profile, what it looks like. This was nice and useful. It's useful to me because it's in my software. But when the engineers needed to use it and stuff, I actually popped it out into Excel. So the information all went into Excel using just a regular graph. They can actually put the profile in. Now, this is really nice because they could annotate it and everything. But the other thing that came up was different projects, same process. But they actually found that they could actually make very nice cross-sectional diagrams. They could put more information on them. So this is a sewer, that's the ground. Each of these going down is a manhole, that's a reservoir. These are house basements. So we're actually able to do that in a nice, easy to use way that didn't require a lot of people calling CAD guys up, getting them to do this. We do a lot of work with municipal drains. So all of these municipal drains have been documented for a while. But what we did was we actually took the scenario in Niagara as well. And what we did was we actually worked out a calculation that traced out where the drains should be or where it thinks that they are based on the elevation information. One of the really nice things was it actually worked out very well. Most of them were actually in the right spot, or sorry, I should say most of the previous data was in the right spot. So we were able to actually use this as an update. So this is a nice way that we can actually work with some of the environmental groups to make sure the drains are working properly. It also works out well because when we can actually look to see how the drains are working, if there are any environmental issues, we can usually trace it back to see where it came from, what drain it went into and stuff. So we do work with the Civil and CAD group. So this is the Port Colborne water treatment plant. So it's just a layout of it. I can't see it too well, but this is basically the same information CAD. So when we actually got this digitized and put in, we sent it over to the CAD guys so they could actually do their design. Then also to help out with the CAD group, with the Civil group. So I think I saw BIM as one of the potential options you guys can work. So yeah, so this is actually a Revit model that we're using. And it's for another water treatment plant. But we made it using LiDAR. So again, we have terrestrial LiDAR that we set up. We actually scan everything. It pulls everything up very nicely. And you can even see how we can annotate it. So we'd actually have, excuse me, we do actually have areas where we have assets that have been located. And these two things, those are not pictures. Those are actually the scan points. So every time we scan, every setup, we collect about 40 million points, give or take. Each of these two scans, which are actually a very small area, those probably had about 8 setups. So you can imagine how much the whole plant had. But yeah, so we can use that. And then as your one professor was discussing, this is actually the power station. This is the old power station in Niagara Falls. So this is a Century building. It came online in 1904, I believe. But they actually turned into a bit of a tourist thing now. So you can actually go through, it's a bit of a museum. It's very, very cool. So what we did was we actually scanned all of that, and then we generated a 3D CAD model. So using this, they were actually able to determine, what changes they need to make. They actually built an elevator that goes down in there. So they were able to check out, is the shaft correct, all that kind of stuff. We actually, when we did this, we actually did it in 4 parts. So the main building is 1 part. It's actually got 3 basements. We did the main shaft, which is 160 feet deep. We did the forebay. They actually drained the forebay for us. We could actually scan that. And then one of the tunnels that now is a tunnel that you can actually go out as a service tunnel to watch the falls. But it was actually one of the penstock tunnels before. And it's a little bit more 3D stuff. So this is actually these are both landfills. So this is actually a volumetric analysis. So the areas in red are areas where they're above their cap. The areas in green areas where they're below. So they actually figure out what the cut and fill ratios are. This is another one that we were doing similar calculations. So again, we've got another profile on the bottom. This one was done with LiDAR. This one was done just with regular surveying. And one of the operations that we did once was we had to find a good spot for a water tower. So a lot of people don't like the idea of a water tower being put near them. One of the questions that came up was how much shadow is this water tower going to cause? So we actually did an analysis with this. So we actually had a little animation. So you can actually see how much shadow this water tower is creating. So this gentleman who was concerned about having his house in shadow and stuff, we were able to show him that actually it won't really be in shadow. Even if he does have shadow coming down his driveway, we're only talking 30 minutes of additional shadowing. So we do a lot of model building for the analytics as well. Web mapping is becoming a pretty regular thing. Web maps don't just need to be regular maps, though. They can even be electrical diagrams, things like that. And interoperability. So this is where we're actually using web services. So none of this information resided on our servers. This is all stuff we brought in from other people's servers. So we were able to bring that in. This is work that we did hooking up to someone else's Oracle database. And then this is just some of the background data being hooked up from SQL Server. So a bunch of the other things that I work on with all the data. So bridge inspections is a big thing. So anyone's interested in bridges, you have to do bridge inspections, road needs assessments, PACP evaluations. So that's for sewers, manholes, street lights, facilities. You can read them there. But one of the nice things I really like about what I do is that I do get to work with like all of the disciplines, except for electrical. They're the only ones I don't really work with. A couple things to keep in mind when you're working with open source software. Like say some of the pros, it is faster in terms of adopting things. You can often customize a bit more, has good community support. Some of the cons, sometimes support can be challenging. So you do have a question, you don't necessarily have someone you can go to. Sometimes new versions can introduce new bugs. I haven't really had that problem though. Sometimes it can lead to branching. So sometimes someone will want to take a project and go in a particular direction with it. Totally can. It's open source. One of the fears is that, well, what if they stop building it? Yes, that can be a problem. However, I could look at BlackBerry, who also, no one ever thought they would stop me. So just as a bit of a conclusion, like I say, it is another tool from toolbox. Data is very important. How it works into engineering, civil engineering is very important. Using things like open source alongside other applications and tools, it's a great thing. You can have a lot of fun just experimenting, playing around with things. And it's more important of what you're trying to do and how you're trying to do it. I do get some clients who come to us like, no, we have to use this application to do something. And I kind of ask them, why do you have to use that application? And they never really have a good answer. They like, sometimes they want to justify the, justify the cost of it, and that's it. So, any questions? Very much. Oh, sorry. It all comes into the same spot. So a lot of structural design is based on basically meeting structural needs, like this building, capacity, people, that a lot of the architectural things that you'll find, they're looking more at the function, or sorry, more at the form of it, less at the function. So the two things are basically two sides of the same coin. All the data though, we look at the data the same way regardless. So it comes in, we look at the equations, we look at whatever it's trying to satisfy, and basically see like, does it actually work, the way it's supposed to, the way it needs to. Yeah. Bridges are cool too. Okay, thank you very much.